One of the deep and crazy things that Orsted has discovered that Ampere is making a rigorous mathematically, but seems weird to people is that the static electric charge don't make magnetic fields. They don't interact with compass needle, but moving electric charges do. So as soon as you have a current flowing, then you have a magnetism in the room. This is very weird. Let's think about very mechanical analogy. So suppose you have a balloon and you have rubbed on your shirt, so it's highly charged. It created an electrical field, and other electric charges will respond, but the magnets will not notice it. There is nothing magnetic about it. There is no magnetic field in the room. Okay, so I'm sitting in the room and there is a room. I'm insisting and quite confident that I have experimental evidence that with my compass needle that there is no magnetic field in the room. Now I want you to enter the room in a slightly different reference frame. Remember, we've argued it's basic Newtonian idea that you can observe the world in any inertial referential frame you like. You can be sitting away from me and make your measurements. You can even be moving with a constant speed in a straight line with respect to me. So you are in a little car. No. So you're in the little cart and you are cruising into the room. You go past me and you cruise out of the room. Let's say you are moving at steady 2 meters per second. You're in this little cart, and now in your reference frame, you would consider yourself to be at rest. This is a critical idea about reference frames. You're in the cart. You're in the cart, and everybody thinks they are at rest. But what you see is you are at rest in the cart, and you see a room slide by you at 2 meters per second. That's right. You see me slide beside you holding a compass needle. Well, so you see a balloon side by you. Think about that balloon. You see an electrical charge moving past you in your reference frame. A moving charge is an electric current. Electric current is nothing more than the moving charges. So you see a current in the room and you say, according to the Mr. Ampere and Mr. Orsted, if there is a current, there will be a magnetic field. You pull out your compass needle and sure enough, the compass needle changes its orientation as the balloon goes by because that's the direct evidence that there is a magnetic field in the room. So you and I are standing right next to each other. You pass right by me, and you and I disagree about this fundamental statement. Is there or is there not magnetic field in the room? So this is a kind of wild idea that is leading us to a much deeper understanding of the principle of the relativity. First Galileo's relativity and later Einstein's relativity. Yes. What we are saying is that yes, electrical fields are very real. You can see them, you can see them, though they are a little bit tougher to see. You could sprinkle glass seeds that are electrically polarized and see them, right? So you can see magnetic fields with a piece of paper and iron fillings. They are definitely there in the room, and yet you and I can disagree about the strength of the magnitude of the field. That now that's kind of a weird idea. Then you just say, okay, I guess that's right. You and I disagree about lots of things. We are in different frames, reference frame. We disagree about positions. We disagree about velocities. We apparently disagree about the strength of the magnetic fields, that just as we disagree about the strength of the meter per second, right? So there are just numbers describing physics. What we agree on the rules. We all agree that moving charges create magnetic fields, okay? Stationary charges create electrical static fields. every law of physics that you and I come up with is in complete and in complete and total agreement. We discovered that mathematics Ampere developed, and further physicists beyond him are developing approaches to how you connect the value in the two different reference frames. It's pretty simple and straightforward. So this is a connection between electricity and magnetism that's really profound. Yes. So think about this for a second. I am in a room that only has electrical fields. You are in the room that has a magnetic fields, and yet we are both in the same room. It's a same space, so electricity and magnetism seems to be connected to one another in an intimate way. It just depends on the observer whether you call it electricity or whether you call it magnetism. That's really the cool, the deep idea that people are developing here. Electromagnetism is a name we are going to ultimately give to this one force of nature that just has two sides to it. Wow. Let's go back to the applications. Okay. The magnetic fields that are produced by an electrical current are ordinary magnetic fields. They are exactly the same as the magnetic field from the kitchen magnet or one of those toy magnets. And it's really a universal law of nature that we are discovering here. If you have a certain current, you will create a certain magnetic field strength. A compass needle will twitch with a certain strength, and if you double the current, think of the superposition principle. It's just like having two charges following per second instead of one, and that's going to make 2 times as big magnetic field, which is a part of what Mr. Ampere is writing down in his mathematical formulas. So if you double the current, you double the magnetic fields. Now you're starting to think applications. What if I want a really strong magnet? What if I want to be able to lift car up at the junkyard, and a car that has some iron in it? I'm never going to be able to go to the beach in Greece and find a lodestone big enough to do that. What I'm going to do instead is I'm just going to flip a little switch that makes electricity flow, and flow electricity is going to create this magnetic field. It's going to lift up the iron core, and I can turn it on and I can turn it off. Think of the technological power of this, because manipulating electric circuit is quite easy, and then you can do these mechanical things with it, right? Sure. So you can sit in your car and take the metal key, insert it in the slot and turn that metal key. And what is going on? Well, you've now reoriented the metal so that it touching some other pieces of metal inside jacket and you've completed a circuit. Wow. This is what happening. Okay. Well, you've now reoriented the metal so that it's touching some other pieces of metals inside the jacket, and you completed a circuit. Wow, closed circuit. Now electricity is flowing, and the electricity flows through a coil of wire called solenoid, which makes a magnetic field that is strong enough to pull a little iron rod. Wow. So this is how you start your car. In old days, you had to physically, mechanically turn a crank, and you are letting the electricity turn on magnet, and the magnet does the pulling. Wow, the great manipulative power of this basic law of physics. Wow. So if you want to understand magnetism, now you ask the question, what about the kitchen magnets? Yes, this is my question. I was just arguing that magnet arise because of the electric current. You can turn them on and you can turn them off. So what's the deal with a kitchen magnet or with a toy magnet? That's a nice story too. We can make sense of it. But to make sense of it accurately and completely requires some quantum physics. the classical story is good enough, okay? It's enough. It's a nice, simple explanation. Let's think microscopically. We have some material object, and it's made of atoms. Atoms have a positive and heavy nucleus and little negative electrons running around the outside, a little electric charge running in a circle. That's a current, and the current has a definite direction to it. It's going around in a circle, and according to the Mr. Ampere's law, that's going to create a little tiny magnetic field. It's not a battery that makes it happen. Anytime you have a moving charge in the nature anywhere, it's a universal. Any moving charge creates a magnetic field in a very well-defined way. Little atoms create a little magnetic fields, which means that the atoms are little tiny magnets. Now, imagine that you have one atom here and another atom right next to it, and maybe the electron is going clockwise in the one of them and counterclockwise in the other. It's three-dimensional, so it's three-dimensional, so the little magnets are totally randomly aligned, okay? And they are very close together, so you have an up magnetic field from one atom and a down magnetic field from nearby atom. Up and down cancel. It's a superposition principle applied to magnetic force, just like any other force. It's just a Newtonian or Galilean superposition, right? So ordinary materials aren't magnetic because the atoms are randomly aligned. Ah, yes, I got it. All of the little micromagnets are randomly aligned. It requires very special material, one in which the electric current of the one atom couples or connects to its neighbor in such a way that the two magnets tend to line up. Iron crystals microscopically are so iron crystals microscopy are such that the atoms tend to line up their magnetic field. Now, how is it that you can create a magnet out of the iron? Well, you rub an existing magnet against an iron bar, and as you do so, you are creating a strong magnetic field that begins to line up all of the atoms, because after all magnets like to line up with other magnets. Once it happens, you have a cascade because each atom's magnet talks to its neighbor, which talks to neighbor, and there is this sweep through the iron as everybody lines up. Now you step back and look microscopically, and you see the whole bunch of the little itsy bitsy microscopic magnets that are all pointing the same way. You have a magnet in the laboratory, and once they are lined up, they tend to stay lined up, and there is no electricity required. You don't have to have a battery to make a kitchen magnet stick to the refrigerator. Haha. Okay. Fair enough. So there is this natural or automatic way of creating a magnet, or this artificial way of driving electric charges through electric circuit. You see electric fields to push the charges to make them go in a path. So there are these multiple ways of thinking about magnets that are really ultimately all the same story: moving charges. Now we've argued that static charges do not make magnetic fields, but moving charges do. We've also argued that static magnets do not make electric fields, but what about moving magnets? It's a natural question to ask. It seems like gosh, if the universe was symmetrical, moving magnets should make electric fields. This is what Mr. Faraday investigated. One of the many wonderful experiments he did was to take a magnet and to move it rapidly, to jiggle it. Any kind of motion will work, and by the way, you should appreciate that these effects are fairly subtle. When I told the story about moving a balloon making a magnetic, the field that would be an extraordinarily weak magnetic field. If you move a very, very powerful magnet rapidly, you might just be able to notice this effect in the laboratory. This is Faraday's discovery. It's perhaps the most practically important applied physics discovery in the history of the modern science because you can wiggle a magnet and create electric field. Think about what you can do. You can make electric field. That means you can move charges around. That's what we want in our houses. Wow, 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 wow. So where is the electrical field coming from that pushes the electrons through your toaster oven, or through the lamp, or through your computer? Well, somewhere out of town, there is a power station and it has a big giant magnet. It has a big giant magnet, a physical giant magnet. Somebody is turning it, and it might be windmill turning it, it might be a steam engine turning it, but there is a big magnet that's turning near the metal coil. The changing magnetic field is driving electrons, pushing them and all the way to your house. It's a direct physical connection. And it's this entire symmetrical story that electric and magnetic fields are indeed, after all, intimately connected to one another. One of them can create the other, not statically. You have to have motion. But as soon as you have a motion, meaning you have to have acceleration to push it. Okay. But as soon as you have a motion, moving charges make magnetic fields. Moving magnetic fields make electric fields. Beautiful symmetry. We are going to want to come back and tackle this symmetry. It was the work of James Clerk Maxwell to recognize how elegant and beautiful this story ultimately is. Haha.